I looked at your, Slack post about
Yeah.
GADTs basically not being functors, and I'm still thinking about it. Is there a way to do it where you might consider it coming from the category that has just those two sets in it, but just my intuition is that it probably isn't going to work, because if anything, it's totally not parametric.
Yeah.
Parametrically polymorphism, because they're basically casing on the type and doing something different.
Yes.
So
yes.
So I'm thinking that if you had a GADT with, a parameter that's the type, and then the index could be something else, that it probably is a functor on that parameter.
Yeah, I mean, you could have more than one type parameter, and some of them. So you could have a GADT that has an extra type parameter, or many of those.
Right.
And with regard to some of them, it could be a functor.
Right.
But with regard to others, it will not be. And then you will not be able to use parametricity for that. But you will be able to use parametricity for one type parameter for those type parameters with respect to which it is a functor. So basically what you do is you fix all other type parameters except one. And then you can have parametricity with respect to this one. Or you could fix some of them and leave some of them free. Then you would have parametricity with respect to several type parameters at once. But you could not do that with respect to the index, as you say.
Right.
So then no, that's the whole point of having a GADT.
Yeah, I think so. So that it isn't parametric.
Yeah, and that's fine. So that's in fact you could have a category that just doesn't have any arrows, and then it will be still, formally speaking, you could have functors in there, it just won't have any arrows. So if you don't have any arrows, then you don't need to have parametricity with respect to the type parameters.
You don't have any relations.
You don't have any relations. All relations are empty, and so you're kind of trivially having parametricity, but it won't give you anything.
Right. But so like the vector type, which is parameterized by like type A, and then it has the index, which is the nat. And I think for each index, if you fix the index, then it will be a functor on the A parameter.
Right. So you can
That's
do
pretty
that.
much what you were saying. As long as you fix everything else, it'll be a functor.
But with parametricity, with parametricity you can do this. You can fix some type parameters, and then look at only consider them as fixed, as some fixed types, and then you do not vary them, and so you do not have any laws with respect to those. Those are always fixed, and so you can have then still relational laws or naturality laws with respect to other type parameters that are not fixed. So that nothing prevents you from doing that in any case.
Right.
So right. So anyway, let me see if I can share my screen. No, start broadcast. Let's see. Okay. Right. So I was trying to figure out this derivation here, but I did not figure it out. Well, I didn't have enough time. Anyway, so we stopped. I don't know where did we stop?
Yeah, good question.
Here we stopped somewhere, right? And actually, at the end of the previous meeting, we had a question such as if you had this type and you wanted to show that it is equivalent to this type, then what profunctor would you use? So that I think that's
which
where
are the two types that you're doing?
So the first is
first
this.
of all, what page are we on?
So am I not sharing my screen?
Yeah, you are. I just
You are. It looks like page 9.
Let me just scroll on. Yeah, it's page 9.
Yeah. Okay. Good.
Right. So I think we stopped at this point somewhere, where we're looking at the claims. So the claim of this paper is that you can have a profunctor formulation like this,
Right.
and it is equivalent to a simple formulation, direct formulation like this.
Mm-hmm. Right.
And so similarly for lens and prism, you have these profunctor based formulations which have this form. There's some type class in addition to profunctor. And then you have this type signature, PAB to PST. And that is equivalent to some directly defined type, such as this.
Right.
S to A and SB to T at the same. So it's a product of these. So you have a get and the set in the lens.
Mm-hmm.
In other cases, it's more complicated. And so
Can I pause you there?
Huh?
Can I pause you there for a moment?
Of course.
I think one thing I've been having trouble absorbing is having quantifiers in my type descriptions, right? Like the ones that you have highlighted here, right? So yeah. It's not something I'm used to, having a universal quantifier for all P, the beginning of that.
Yeah.
I think I know what it means. I think it means basically that whatever code implements that function, in addition to being allowed to use the fact that P is a profunctor, it has to work for any profunctor P. So it can't do anything arbitrary beyond knowing that P is a profunctor. Does that sound plausible?
Yeah, I think that's right. You might think of it as being a function from, the stuff that makes it a Cartesian, so the second and, FMAP operations, you're going from those operations to that, to that function between PAB and PST.
Yeah.
You know what I'm saying?
I think I do. Yeah.
So the P is sort of, yeah.
Well, I would add to this. So there is an extra type parameter here, which is the P. On the left, you do not have that type parameter.
Right.
So how would you create a value of this type? In fact, you need to create a function parameterized by A, B, S, and T, that because you are given those, but you also need to have a function parameterized by P. So if you write code for this, how would I implement a value of type? So let's say X has this type for all P, P, A, B, P, S, T. How would I implement a value of X? So I actually need, well, in Haskell, you don't write type parameters. In Scala, you do. So in Scala, you would have to write def X of.
Be right back.
Okay. A, B, S, T, and P.
Mhm.
And in Scala, you would write P with two type parameters itself, because P is a type constructor itself. And then you would put arguments on this X, which is some kind of whatever, N of type P of AB. And that should return a value of type P of ST. So the fact that you have this quantifier means that when you implement a value of this type, this value will have an extra type parameter inside. But outside, you don't see that type parameter. So in other words, it is not given, so that this should work for all P. But it only works for specific A, B, S, and T, which are given here. But it is, so this is an extra type parameter that needs to be introduced. And of course, the type class here means that there's some extra data that is given, such as DIMAP and second. So these are given also as arguments to this function. So this function X will actually have extra arguments, not just this argument N, which is P of type PAB, but in Scala you would have to write explicitly the DIMAP and the second somehow as arguments of this function. And so what I would say is that whenever you have a type signature of this kind, you have to think, well, now I have one extra type parameter. So then the question is, why would that type parameter not be on the left-hand side? And it can be, except that in Haskell, well, it's not easy to, well, I'm not sure if that's true, but I think in this case, it can be on the left-hand side. But
sort of their notion is that a lens is pretty much parameterized by ABST.
Right. So you want to compare, you want to be able to compare this directly with this, and this directly with this, where the P does not appear. So you don't want this P to be given on the left for this reason. But it can be rewritten equivalently as like here, type adapter P B A B S T. But then you would have to say that P must be a profunctor, which is not so easy to write down. So does that help?
Yeah, it does. And the other thing which I didn't realize until I read this several times was that they're actually defining a mapping from, let's say, there are three cases. The first case is a mapping from what is it? Adapters to these things, profunctor
also
adapter representations. Right. So any adapter should give you a profunctor adapter representation by the same technique that they use for this flatten example. Is that right?
I'm not sure. Say that again.
Yeah.
Not following what you're saying.
Yeah. So I mean, ultimately, they're going to argue that adapter P is the same as adapter, right?
Right.
Yes. Right.
So that, but in particular, if you have an adapter, it has a profunctor representation, right? It has one of those adapter P.
Yes.
One of the associated, and that's an actual mapping, right? So
yes.
any adapter will give you an adapter P.
Yes.
Okay. Yeah. And
well, they're claiming that these types are equivalent.
Yes.
Which means that there is an isomorphism in both directions.
Mm-hmm.
So any value of this type is mapped into a unique value of that type, which is mapped back to the same value of this type.
Yep, and the direction, and they give you the map in one direction.
They do, right?
And yeah.
Now they do not. Well,
later on they prove that adapter P and adapter are equivalent.
right.
Yeah.
Now this is just a specific example of an adapter. But so yeah, so this is their claim. So there are these perfunctor-based definitions, and there are non-perfunctor-based definitions. And the main claim is that they're always equivalent. You can always find the perfunctor-based definition for any of the ones that people have found independently.
Cool. Thank you. That's good to, confirm.
So yeah, and so one question that we got stuck at the end of the previous session was just quite concretely, how do you go from here to here? Because from here to here, it's kind of easy, because if you have this, then you can map a profunctor AB to profunctor ST and just have a die map. You map A to S because you have S to A function, and you map B to T because you have B to T function. And in the profunctor, the first type parameter is contravariant and the second is covariant. And so going from here to here is easy. But going from here to here did not seem to be easy, because how do you extract this from here?
Can you use the identity profunctor P?
Yeah, that would be the obvious thing to try. If they're like,
so what's
there's a trivial profunctor, can we plug that in?
So what's that? What is the trivial or identity profunctor?
I guess it has to work for any A, B, S, and T, right?
Well, profunctor only has two type parameters.
Oh, right, okay.
This whole thing is parameterized by ABST, right? So we kind of consider them fixed, but the profunctor in going this direction is a for all. So we get to pick it. And I think we pick it to be the identity. And
so what is that? What
like
is
you
the
were asking?
Yeah. What is the identity profunctor? How do I write it down? And so we could not figure it out back then, but I have an answer now. Okay. And the answer is, so you want to have S to A, B to T out of this. And the only way that you can do this is when you apply this function to something. Because this function itself is a function, is not like this, it's not a product. So you have to apply it to something to get this. So my initial error was that I was thinking that I would just substitute some P in here and get this, but that's not true. So you need to apply this function to some value of this type, and then you would get a value of this type, and that value should be this. So that's the trick. So what is that value? So let me copy this over there. So advanced technology. And let me drag it over there. And put it over here. Oops, Okay, so I only copied this stuff. Okay, good. So this I will have to write by hand. So what I want is that after substituting some p and applying to some PAB, the function will give me the right-hand side. So PST must be equivalent to S to A, B to T. That's the trick.
Hmm.
So P is a profunctor that actually depends on A and B. So Pxy is equal, by definition, X to A, B to Y.
I'm sorry, I don't see how you go from the line 1 to line 2.
Well, you're kind of going in the reverse. So we're trying to figure out what P has to be in order to make line 1 work.
Yeah.
Something. Right.
Yeah, we want this. We do not, we cannot derive. But what we want, first, we realize that we have to apply this function to some argument. So there's this function, we have to apply it to some value of this type. Once we do that, we will get a value of this type. And that should have the type of our required result. And so
that's what I don't see. Isn't the whole type for all P, PAB, arrow, PST, that is what's equivalent to the right-hand side, right?
Correct.
So if you apply something on the of type on the left side to the argument, why would you get P of ST is not going to be equivalent to the right-hand side? I don't see that.
Why not? So that was the problem that I had. That was a difficulty that I also had. But now I think I can resolve it. So why not?
Okay, that's like saying if the left-hand side was X arrow Y is equivalent to the right-hand side, then you're saying Y is equivalent to the right-hand side?
No. Y is not equivalent. I'm trying to write down the isomorphism. So I'm given the value of, okay, so let me.
So actually, we're not doing isomorphism here. We're really going in the right direction. So, right, we're trying to come up with the function that goes from the left side to the right side.
Yeah. So we want. Okay, let me try to make this a little easier. So we're given a value of this type. We want a value of this type. Right? How do we get that value? So we say n equals m of some kind of q.
Okay.
Where q has type PAB.
Okay, that's assuming that we've already specified some P, right?
Yes, we have to specify what P is.
That's what Q is, right?
We have to specify what Q is.
Okay.
We still haven't done it, but this is the plan.
Okay.
Well, isn't the plan to then apply that to something else? M of Q will then get
M of Q will be n.
Okay.
So we expect that this will work. This will work. How do we make it work? So
and A and B are already fixed. So the only thing the only leverage we have is to choose P. We need to choose some profunctor P.
That's right. And so I claim that this one works.
So you also claim that it's a profunctor in particular. I mean,
Yes.
it's clear that it works because if we substitute S and T in for X and Y, we do in fact get.
So first of all, let's find out what Q must be. So Q must be of type PAB, right? Which is the same as A to A times B to B. See, so this was the secret power here. So now obviously we can write what Q is id times id.
Or id comma id.
Yeah, sorry, this is not Haskell.
So it is an identity. We were right about
A
that.
pair of identities.
Yeah.
Well, no, the Q that we substitute in this formula is the pair of identities. The profunctor P itself is
Not an
defined
identity.
like this.
Right.
I don't see any identity in here. We need to define a profunctor. So we define it.
Right. So it's not the identity profunctor. I was wrong.
Yeah, and I don't even know what
that
would be.
That profunctor, yeah.
So it is that profunctor. Now we define it, and it depends on what A and B are, obviously. But A and B are fixed, so we are allowed to do that. So
in some sense, when you say expect, it's like n equals m, and then kind of like in square brackets. You know, because we're not sort of specifying what P is anywhere, which is a little confusing. But
okay, well, if you wanted to write it in Scala syntax, then you would write it indeed like this.
right. Okay.
Right. So in Scala, you can, in Haskell, I think you would write something like this.
Okay.
So with an
Let's
at
do
symbol.
it with the cat.
But anyway, so this is the idea. So the idea is that we will specify P like this, as line 3, and then we will be able to compute N. So if we apply M to this value Q, so we apply M to Q, Q is a fixed value, which is well defined. Then we get a value of type S to A, B to T, because that's what N is. So that is then equivalent to PST. And that's the whole thing. So we have found how to compute N from M. And that's what the whole point was.
I still don't see how, okay, the definition of M of that type and N of that type, but then N is equal to M applied to a Q. I don't see how that can be the same.
What do you mean the same? Sorry, what is the same? We don't know. We don't have any same right now. We are given some value of M.
Yes, right.
We should find some value N of this type. We don't know which one we need to find.
Correct. But the way you're trying to do it is you're applying M to an object of type, object Q.
Yeah.
Okay. And that gives you an object of type PST.
Yes.
So how is PST equivalent to the type of N? That's what I don't get.
If P is defined like this, then PST is the same as this.
I see.
So that was the whole point.
But then aren't you assuming the result here?
No.
Or is it because we are free to choose any P that is a profunctor? In particular, we'll pick this one.
Yep.
Right.
I see.
Right. So the whole trick is that it's not easy to find this P. But we are allowed to take any P we want, and this P could depend on A, B, S, and T if that's necessary.
So going back to line 1, you've taken the left-hand side and you've done some transformations on it to come up with the right-hand side of the equivalence.
I have not done any of that. No.
Wait,
Actually,
you
no.
said given something on the left-hand side of the equivalence, you can construct something on the right-hand side.
Right.
That's a
what we
yes, but this is not yet equivalence.
No,
I'm
but
just
you've gone
doing
from
one
the left.
direction. Yeah, it's
you've
one
gone
direction.
from the left
Yeah.
to the right.
Yes. There's one direction. Yes.
Cool.
So yeah. So what's your question?
No, I didn't have a question. I just want to make sure I
Yeah.
understood.
Right. So right now, all I'm doing is I'm showing how to find a function that goes from this to this type. And the function that goes back from this to this, it is easier. This is just die map. What remains to be proved, if you want to do it this way, you can still, you can do it this way. What remains to be proved is that if you take some value of this type, some m, then you compute n out of it using this formula, and then you go back and compute another m out of it, then you end up with the same m you started with. That's what you still have to prove here.
You're talking about the fact that the round trip has to be the identity.
Yes, right. Because if you don't show that, then you have not proved that you constructed the isomorphism.
Do we know that our maps are functorial,
Natural.
or preserving all the structure that they need to preserve?
Well,
I'm not sure what that structure is offhand.
so, I mean, yeah, for example, you can say, well, okay, I have this going into this, but what if I now map A to some A prime, and I also here map A to some A prime? Is that consistent?
So it should be natural in all of
Right,
those.
so that's what it would be. So I change A to A prime, so I have P A prime B to PST. Then I have here S to A prime B to T, and I still have the same equivalence. So I have the square, which is the naturality square with respect to A. So this I have to show, and this is maybe that it is natural. And then with respect to B, and then with respect to S, and then with respect to T. I have to show that.
Do we have to also show that P is in fact a profunctor? So for line
P,
3,
you mean
we
this
would
one?
Yeah.
We do.
Mhm.
So there would we have to give the die map that
Yes.
P,
Yes.
or is that obvious?
It's
Well,
almost obvious, I think. Sorry to interrupt, but basically a profunctor is anything which is it has two type parameters. It's contravariant in the first and covariant in the second. That's all you need, right? And just sort of looking at that expression, yeah, it really does seem to be so. But yes, to be thorough, one would have to supply the die map.
Yeah, it's just that die map is well, it can be automatically generated from the type because it's clear that this is contravariant and this is covariant, and then the die map and the laws and everything.
It's just sort of the parametric polymorphism that you just get automatically. All right.
Yeah. So in principle, yes, you have to prove it, but it's standard. So all of these things will have these properties. Yeah. So then you have to prove the round trip, and the Yoneda lemma absolves you from having to prove that, because that proof is not easy, because you have this complicated stuff here, complicated P. You use this function on a specific value to get this, right? Now from this, you get again a function. So is it the same function? So you have to apply this function to an arbitrary value and show that the results are the same and so on. It's a lot of work, and that you have to use parametricity, you have to use naturality, and it's a lot of work. So you can do this by hand, but it's a lot of extra unnecessary work, because, well, Yoneda lemma gives you a proof. Where am I? I think I jumped in the wrong place. I was supposed to be on page 9, right? Yeah. Right. Right. So we were here, and oh, I see. We were here. I should have kept this highlighted. So, right. So basically, that's where we were. And now, okay, so we figured out for this case how to do this. But for this case, it will be more complicated, because now we have a Cartesian P. So we'll have to show that it's Cartesian, but it's essentially the same trick. So you have to find the P so that the result is what you want, and then this will hopefully be some identity functions. So you apply. Remember this. When they said the pattern, you use functoriality and identity in both directions.
Right.
So here the point is we apply this function to an argument that is made out of identity functions. So that is actually this is how this pattern manifests itself when you apply to functional programming. So you, in one direction, you apply the identity function, and in the other direction you use fmap, dimap, and so on. I wanted to maybe give a simpler example of this. So for all C, which is contravariant, C A to CB is equivalent to B to A.
So you're saying it's a contravariant functor.
Yeah, I don't know how to. I like to say contrafunctor, but I don't think that's a standard term.
Well, let's just do it anyway.
Right. So yeah, it's a contravariant functor. So if you have for all f functor.
Is it not a cofunctor?
No, I don't think so. Well, so that is equivalent to A to B, right? So then to show this, you would say, oh, I just put identity functor in here, and then I have identity, right?
Is this the Yoneda embedding?
Yes. Well, it is what they call double Yoneda, I think, in the next section.
Oh, okay.
Where you have for all functor something, and that is being simplified into a type that does not contain this functor. So what I'm saying is that this was deceptively easy, because you just say, I put in here the identity functor, and then this is just A to B. But already for contravariant, this doesn't work. You cannot have identity contravariant functor. You just don't have it, because the identity functor is covariant. Well, in the usual, well, in the end of functors in any case. So here you have the same problem. How do you show that from here follows this? And you show that by defining a special contrafunctor, which is x to A.
Oh, okay.
And so
So
then,
then it'll be A to A. And
right.
that's the
So then
identity.
here will be A to A. And here will be A to B, B to A.
B to, yeah.
So then CA to CB is the same as A to B to A. So A to A is identity. You put identity in here and you get B to A. So it's the same trick. So the trick is that you have to apply this function to a specific argument with choosing a specific contrafunctor, and then the result of the application will have the stuff you want. So this is just a simpler example of the same thing.
Mm-hmm.
So the interesting question is that complicated types like these are somehow encoded by these type classes. So there's some complicated stuff, you know, getting and setting values in a lens or prism and so on. And somehow these things are encoded by a type class on a profunctor.
So probably it's going to, you know, be a PST. We're going to define P so that PST is that lens.
That's right. PST must be that.
And the definition of Cartesian has to do with products, as I remember. I mean, it's not completely out of left field, right? We need to produce something with lens that involves a product, right? That's the new wrinkle. There's a product involved.
Right.
The definition of Cartesian also has products in it. That's the thing that it adds. So I assume that that's what's gonna.
Yeah, but this is kind of not easy, right? You have this S to A and SB to T, and that is supposed to be PST, right? Okay, well, you can define P like this, certainly. PXY equals X to A, XB to Y, right?
Do you want an
Now,
X
is this
in there?
Sure. Where?
It's the product of the two things in parens.
Right.
There's a little product that goes in there somewhere. Yes, thank you.
Yeah, thank you. Right. So, okay, so this is a profunctor, that's fine. But is it Cartesian? And I don't know, we have to check how to define this. So you have to have PXY going to PCX CY, right? So can you do that? And it's not obvious that it is Cartesian, but maybe it is. But suppose it is Cartesian. So then what is PAB? It is A to A, AB to B, right? So now this is this you can construct as identity, and this you need to, I guess, ignore A here.
Right. Basically use, yeah.
All right, and then you have identity.
The second projection.
Yeah, the second, right. So, okay, so then you can construct that. And so this is how you would do that. But then to me, it is not obvious that this is Cartesian. You have to check. I don't have a lot of intuition. And to me, this is not obvious that it's Cartesian. But I guess, yeah, you can check. You have to implement and check the laws.
What is the signature of the second? You have to supply the second function, right?
Yeah, this is the signature of the second.
Oh, that is, okay, got it.
So yeah, So you have to implement that with this P. So maybe you can. And then, but you see, this appears to be very much ad hoc. So this is, it's not clear why. To me, the mystery here is that you have a quantifier over all Cartesian, and somehow that gives you the right things. So why, you know, here we had a quantifier over profunctors, and it gave us this instead of S b to t. So this S in here was inserted just by putting a Cartesian. How can that, how does that really work? So anyway, so that is the mystery. Okay, so I can stop here and somebody can continue.
Do we want to
So-
try and figure out how to define second, or just go on? I don't know.
Well, I would be for it. So is there interest for this?
Sure.
So if you
So-
expanded the right-hand side of that, what would it be? It would be something like C cross CY.
So what is that? It is, first of all, CX to A, right?
Cross.
And then CXB to CY. That's what it looks like to me.
Okay. And so we have to give a value of that
Yeah.
thing, and
We're
then
given a PXY, so given,
right.
so we want this, and we're given PXY, which is X to A, XB to Y.
Okay, well, the first component is easy, right? That's the trivial one.
So we ignore the C.
Right, so we take CX projected onto the X, and then we use our X to A to get an A.
Right. And this one, we put C in here. So we just don't do anything with that C.
Right. Just carry it straight
Oh, yeah,
through.
okay, yep. And then the XB we can feed into our given function.
So we can
Y.
get that. Right.
Yeah.
Okay.
But then, okay, so there are a couple of laws to check, and the laws are a bit hairy.
Yeah, well, the laws, so for example, if instead of C, you have a product like CD, then this should be consistent. So you first get from PXY to PCX CY, and then you add a D on top. So you have a P DCX DCY.
Yeah.
And it should be the same as if you added DC at once. But this seems to work because we're just ignoring this C. So we can ignore any number of those. We ignore D,
Right.
ignore C, right?
Yeah.
And here we just put them in as they are.
Just
We don't
carry
do
it
anything.
through.
So we carry it through, and so we can carry C, D, and so on in the same way. So it doesn't matter if we carry them through both at once, or we first carry one of them through and then the second one. So this looks like the laws will hold. And if this is a unit type, then obviously we haven't done anything. So it's the same function. ignoring a unit type, it's the same function as not ignoring a unit type. So
basically not using C, really, it's either ignored or carried through. So it doesn't matter what it is. It's something.
Yes, right. Yeah, and so by the way, okay, so now I think this was instructive, because now I think I have an intuition about what Cartesian is and what co-Cartesian is.
Okay.
In other words, what profunctors are Cartesian? So those profunctors, so generally, profunctor x, y, it must be contravariant in x and covariant in y, right? So what kind of type expression can it be? Well, x must be to the left of the arrow. And then it could have products, co-products, whatever. And y must be to the right of the arrow.
Right.
Or it could have just y like this. Or it could have a product as well. So it's some kind of type expression that's made up of products, co-products, and x is to the left and y is to the right. Right? So that is profunctor. But Cartesian means that we should be able to get a C through it. And the only way to do it is either if we can ignore the argument which has this extra C, but that means it must be on the left of an arrow. So it must be contravariant. We would not be able to do that if the C were on the right, because we cannot create values of type C out of nothing. So it means that, it means that we can have X contravariant, that's fine, but Y should be always in this situation where on the left there's some X somewhere. So the only Cartesian profunctors are those where you have some kind of X going to Y.
Right. So Y is optional, but X is not. If Y is on the right-hand side, then there has to be an X.
Yes.
Right.
So X could be on the left, that's fine.
Yep.
But Y cannot be on the right. So this is not fun. This is not good.
Yeah.
So why cannot just, for example, you cannot just have like some kind of, R to Y.
Right.
Where R is a fixed type. It must be an X. So you could have, R times X going to Y. That's fine, but not that.
Yeah.
So that's the intuition. So Cartesian means that if you have Y, it must be on the right of an arrow having X somewhere on the left.
It's kind of, is it like that because we're going to stick a C in there? It's like, it's going to, it's going to be C cross X going to C cross Y. Somehow you got to be able to do that.
Right.
And I imagine you could throw in other types too, right? Like,
yeah, that's what I mean here by ellipses. So you can have
like booleans, integers, strings. You can throw those in.
You could have other fixed type parameters. You could have, for example, more than one X here. You could have other stuff.
Probably like X cross X.
You could have Y cross Y. You could have any kind of. You can have Y plus Y. You could have, X plus X, whatever.
If you had Y cross Y, would you have to have X cross X? To the left of the arrow. I think you would.
So.
Because, no?
Because you can always duplicate the single C into multiple places, right?
Yeah. I don't think that duplication would violate laws.
Right.
If you duplicate, then you duplicate all of these CD and so on at the same time.
Mm-hmm.
So it doesn't. So if you ignore, you can ignore multiple times. It's okay. But yeah. So I believe that this is the condition, and so co-Cartesian is the other way around.
Mm-hmm.
If X appears, Y must follow. So you have X cannot be X going to some, R. Like we had here. Here we had X going to a constant type.
Yeah.
This is not allowed for co-Cartesian.
Right.
But you are allowed to have R going to Y.
Excellent. Okay.
And so that's my intuition right now. So now you have to show that this is true, but you have to explain what type expressions are allowed. But I guess what you can do is you can inductively construct those type expressions. If you have some type expression which is co-Cartesian, then you can add this to it, or have a product with this, or product of two co-Cartesians is co-Cartesian, for example, or something like that. And then if you want to have a function arrow, then there must be this and there must be that. So, but I'm not sure how you can formulate really. How do you formulate that? For example, if I have a functor fx, that it contains x, how do I formulate it? It's not trivial, that it actually contains some x. I don't know that. But anyway, so but this is just heuristic at this point. So I just wanted to understand what makes this Cartesian. So this P that we defined is Cartesian. What makes it Cartesian? Well, the fact that Y appears to the right of X. So we can always put in some extra stuff.
Does that mean that we could define sort of more elaborate things like lenses using these Cartesian expressions? So we could make a big funky expression which we believe will produce a Cartesian.
No, but wait, why would that be a more elaborate lens? Cartesian here is quantified, so you have any Cartesian here. So coming up with some more elaborate Cartesian doesn't bring you a new lens.
No. What I mean is that, so lens is defined, right, using this S to A, S cross B to T expression,
yes,
which turns out to be like a Cartesian thing.
It's a product of those two things, yeah.
So I'm just wondering about other sort of optics or optic-like things, right?
I think you can make the expressions more complicated, but I think we have to be careful about not introducing the sum, right? We can't you can't, like the left-hand side, S cross A, the Cartesian, the product is okay, but we cannot put a sum in the left-hand side in the domain, I don't think. Because then it does not become Cartesian anymore, right?
You mean here?
Yes.
That's true. It's no longer Cartesian. Yeah.
Yeah. So you can make the expression S cross B, make it more complicated, like S cross B cross something, something, something. But I don't think you can arbitrarily put sums in there or even arrows in there without checking that it's Cartesian again. So
Yeah. So the thing is, in this approach to optics, and each new optic means a new type class of profunctors. So you have as many different optics as different type classes of profunctors. And so if you want a new optic, you need to come up with a new profunctor type class. I can come up with one, but I have no idea what it is for. But I know, for example, the following. So see this second, it is the pxy going to pcxcy, right? So instead of this, now for co-Cartesian, here you have c plus x, c plus y, right? And instead of this, you have a different type constructor with two type parameters, some kind of q cx, q cy. And this type constructor needs to satisfy properties, but if it does, then you have a new type class of profunctors. And I can give you an example of this Q, which makes some sense. So it is X plus Y plus some kind of constant, let's say R X Y. So this is neither this nor this,
right?
But somewhere in between. So you kind of interpolate between product and sum.
Yeah.
Where R is a constant type, and this is another example of what you can put in here instead of this, and then this depends on R. And so you have a type class, a new type class for profunctors, which have this method with this. So pxy going to p qcx qcy, which is whatever called Mogrify, right? And so the Mogrifier is this. And what it does, I don't know, but this is an example of a different type class, which in principle gives you a different optic.
Right.
Which.
So P would be the type class Mogrifier or something like that.
Right.
And,
so it's a.
And this is the.
Mogrifiable.
Okay.
P.
Now,
and then you have PAB to PST. So then I'm just following the same method as was here, right? Putting a different.
But we
type
don't
class.
know what lens that's equivalent to.
Optic, right? It could be not. It could be something completely useless,
right?
And we don't know how to derive that necessarily. We don't know if there is a simpler formulation of this optic. Right, at this point, I know none of that. So what we know is that for specific existing optics, there is a formulation. And so this paper shows you somewhere
like 12 or
like lenses
17.
and 17.
Page 17. Which since you've added 2 pages, yeah.
So lenses.
But I need you to show a guy that your ID.
So anyway, you have, for example, both Cartesian and co-Cartesian, which is a different optic. And then you have other stuff. So
interesting.
But anyway, so or they have zip with great, and have this closed, which is where this Q is a function.
Mm.
Right? So this is closed, and then you have something else. And so anyway, this is applicative traversable. Traversable can be derived as an optic, apparently. And then, anyway, there's these other examples of, so perfunctor existential optics are isomorphic to concrete existential optics, whatever. So yeah, arbitrary perfunctor optics. So this is what they say. There's this D.
Yeah.
And then you have this. Anyway, prism.
So,
prism is, yeah.
Yeah, maybe at some point, I'd kind of like to do some of that stuff, like, starting with the double Yoneda. But my bigger question is why do we do the profunctor optics? Like, why is lens P better than just lens?
So
because it's more composable is what they're saying. But
like, what does that mean?
So what it means is that you have your type defined always in this form, where P goes to in some type class, right?
Mm-hmm.
Now, if you have two values of this type, like that.
Wouldn't it be for all Q?
Yeah, you can write
two
for
of
all
them.
Q if you want to avoid confusions.
I get confused easily.
So but this doesn't really change things. So you can compose them because these are functions, and you can say, well, I always compose them into, for all R, RAB to RUV, right? So, and I set P equal Q equal R, and then I just compose these two functions.
Right.
And the result is that a lens can be composed with another lens, and actually it can be composed with other things as long as they are kind of compatible in going into a small over a smaller type class or something like this. And so the advantage, as far as I understand, is that the composing code is immediate. It's just the composition of functions. Whereas if you take a look at lens, where is the lens? Like here, right? You have this type. It's not obvious at all that you can compose lens ABST and lens STUV. This is kind of complicated stuff here. How do you compose them? And the reason you want to compose them is because lenses are used in programming by defining a lens for a specific part of a data structure. And then if you, for example, you have a data structure with a lot of nested stuff inside, you want to compose lenses into the different nesting levels. So you don't want to have to define every time the lens by hand. And so you want to provide lenses and then compose them. So composition of lenses is important because you want to, you have a lens into another type, which itself has lenses into its parts, and the parts have other lenses into their parts, and you want to compose them. And how do you even figure out how to compose them? It's not obvious, but in the profunctor formulation, it's very obvious. Now, so to me, this is not a very good argument, actually, because programmers will not themselves write lenses. lenses will be written by library authors. And so for library authors, it is not important that it is obvious how to write the library code, or that it is obvious that it works correctly, that satisfies laws. Because library code has other considerations.
But the programmer is like creating this nested data structure.
Yes.
Doesn't he then have to compose lenses, to make this nested data structure work appropriately, or does somehow the nesting of the data structure automatically generate the lenses?
So in practice, you have libraries that automatically generate lenses that you can compose.
Yeah.
But the library
you
also
have to do the composition, but they do right.
But the library also provides the composition operation.
Oh, I see.
You just have to call it.
So they could have a composition that works on lens, not lens P, just lens.
Yeah, because it's a library code. So it's not important that the library code is theoretically obvious or something like this, or theoretically more general. That is not important. It's more important that the library code works fast and easy to use. And so you have some error message with co-Cartesian profunctor not being defined properly or something, with type parameters inside type quantifiers inside type parameters. That would be difficult to deal with for a programmer, and to me it's not convincing that you would actually use this as implementation. Maybe it's somehow okay, but to me it's not really convincing. And also there's a lot of indirection, right? So here you have direct functions, but in the profunctor implementation, you have these functions. So P will be a profunctor that itself contains functions. And so you would apply these functions, and a lot of them would be identity functions. And then you would basically run code that consists of applying a lot of identity functions to this every time. So it's not clear to me that this will be high performance.
Okay. Yeah.
Sorry, go ahead.
No, I'm done.
Did they mention any specific applications of profunctor representations? Because I know when they're talking about, they have some interesting discussion of Yoneda, right? Applications of Yoneda to this, that, and the other. So they have good examples there. And they do talk about composability as a good property of the profunctor representations. But I don't remember that they actually gave examples of it. Did I miss anything there?
Examples of what?
Of like when you would want to use a profunctor representation rather than the plain old optic, rather than the concrete optic. That's what we're talking about.
Yeah, but they don't discuss applications really.
Yeah.
So this is about how you can. Well, actually, I would say this is just an elegant formulation of a bunch of ad hoc constructions in a single way. So you have a bunch of ad hoc type constructions, which
like
were
adapter,
discovered.
Lens, prism,
adapter, great, affine, something, traversal, and these things were invented ad hoc.
But for good reasons.
Yeah, for driven by practice, but they were invented ad hoc, and they actually have different representations, very different representations that are equivalent. and they were invented separately by different people for different reasons. But then it turns out that all of them can be formulated in one way. So, and you don't have to prove anything, because the Yoneda lemma already proves it for all of these cases. So you just have to formulate the correct categories. You have to figure out all this syntax here, which set, and then and so on. And so then you have proved that these things are equivalent, and you've proved them kind of once and for all. So they have this theorem, existential optics, which is kind of one theorem that you prove once, and then you have proved all of these things. Arbitrary profunctor optics. So there's this arbitrary thing, which is always equivalent to some specific optic, which concrete existential optics, which you can write down and sometimes simplify like this. So there's some kind of existential type here, which sometimes you can simplify, but sometimes you cannot simplify. So for the lenses and prisms and so on, you can simplify. So then you don't have the concrete formula for lens, this S to A, SP to T. It does not have any existential types in it, but it has this formulation, which came from here, which was simplified to this. So in some cases you cannot simplify, I guess, and in some cases you can. But in all cases you have this. So in other words, if you're asking what is a different optic that I want to use, then you should look for some different type class of profunctors, which you can plug in this theorem. And you can then have this X optic P, which is this. And, or where is it? X optic shaped. Yeah, so this is the category that you have to define. And then there is some kind of D in which you have this quantifier. And this D is a category of profunctors with additional structure. And for all of those, you have this. So then this additional structure is some kind of shape, which they define. And then you have this class of profunctors, so, which is a specific. So see, we always had things of this type, PAB to PFA, FB, and F is just different. So, FA equals C to A, FA equals C plus A, FA equals C going to A, and so on and so on. So you can have different F, and depending on this F, you have a different type class for profunctors, and then they prove once and for all these F, because F is anything, as long as
it's some sort of shape, I guess.
Yeah, there's some kind of composition law and so on.
Yeah, the paragraph that says define a shape as a family sigma.
Yeah.
Of functors.
Right.
Closed under composition and contains the identity functor.
Right. So for example, this is closed under composition because C times D times A is equivalent to so C times D times A is associative because it's a product. So it's equivalent to C times D times A. So that is what they talk about, closed under composition. And all of this is also closed under composition because C to D to A is equivalent to CD to A. And so a composition of two functors of this shape is again a functor of the same shape. That's what they're talking about. And so that needs to be, if that is true, so you can find some F that is different from those. And I gave you an F before that has a different structure, but I have no idea what to do with it. I just thought it would be an interesting exercise to take a look at that. So that is the main result of this paper, that you now have an interesting way to describe all possible optics. All possible optics is the same as all possible shapes, functors of this kind, which have these properties.
Mm-hmm.
And then you have a construction, which is quite complicated, and goes through these profunctors and type classes, and then this existential thing, and so on, and show that they are equivalent. And then you can show the specific examples that these are equivalent to lenses and prisms and so on. And these are perfunctory lenses and perfunctory prisms. So that is the main result of this paper. Now, why would you want to do this? Why would you want to work with an optic defined in this way instead of working with concrete optics defined by hand? Well, to me, this is a question of more or less, actually, to me, a more interesting question would be the correctness of these optics, the laws that they don't talk about. They say that these laws are, well, I forgot where. The laws of lenses, for example, are that if you get what you set, then you know, if you first set and then you get what you set. The value you can set.
They mention it on page 2.
Yeah.
But they say that the laws don't actually come into what they're talking about, so they're just going to ignore them.
Right. Here.
Yeah.
So, yeah.
But you would want that to be true.
Yeah. Oh, yeah.
They just don't bother to prove it, or?
No, it's just that these representations don't know about those laws. So you actually need to show that those laws hold, and it's not obvious that these representations are directly useful for proving those laws, but they might be. They might be. For example, they say something about isomorphic, naturally isomorphic types. One imposes
well, couldn't you
well-behavedness.
prove it just using regular lenses, and then because they're isomorphic, it just works?
So the question is, would it be easier to prove using this? Because, yeah, of course, what you said is true. You can just take the specific lens type and sorry, it's here, right? This is the lens, S to A, SB to T, and then you prove the laws directly. But actually, these laws would be where A and B are the same as S and T. And then here you would have PAB to PAB. And then maybe you would just say, oh, this must be an isomorphism. PAB to PAB must be an isomorphism. There must be an inverse function to it. Maybe that's the law. I don't know, because they talk about isomorphism, well-behavedness, but maybe this is not. So what I'm saying is that a more important, practically important question would be, does this representation make it easier to prove the laws of lenses, to prove these well-behavedness laws? Or does this representation not help? Is it maybe much harder to prove in this representation? If it is much harder to prove in this representation, and if this representation does not give you good runtime properties for your library, then you would rather not use it. But this I don't know. So maybe this, maybe it is. So for adapters, for example, if you take adapters, right? So let's see where we were here somewhere. No. With adapters here. So if you have adapters, then this is A to A, B to B. And the law of adapter is that these functions, I believe these functions must be isomorphisms. So this function A to A must have an inverse. I think that is the law of adapters, but I'm not sure actually.
You don't actually mention any laws for adapters, do they?
No.
Everything else seems to have laws.
So anyway, this is something I'll have to look at next time, maybe. But right now I don't have an answer for this. So first, so the question is, is it easy to prove lens, prism, etc. laws using lens P, prism P,
using the profunctor version versus the concrete version,
rather than lens, prism. Yeah. So yeah. So what is the law for lenses if you write it in terms of this profunctor representation? And in fact, there are three different, or even, I think there are even four different representations. I'm not sure for lenses.
Laws, you mean, right?
No, representations. What I mean that you can write this lens like S to A, as B to T, and you can write it in a different way. Like there exists Z, like they do in the existential optics, and then something, I forgot what. And for all functor F, something, and for all profunctor Cartesian, something. So there are actually four representations. And the functor one, I think this is called van Laarhoven.
Say again. Okay.
I forgot how it's spelled. I think it's like this. Van Laarhoven.
Anyway.
Representation of the lens. But I forgot the exact part of it. So in any case, the question of representation has come up. They discuss it a little. Formal, proof of the Yoneda. So put get correctness, and here's the existential encoding. This is the existential encoding, which has an extra which is more symmetric, and it has but it has an extra type parameter, which is existential. We have leave for future work, the question of how the correctness of lenses manifest themselves in the perfunctory representation, which might be never coming as future work.
So I guess it's harder since
it could be hard. Yeah, it could be hard. I mean, this for example, it's not obvious why this is equivalent, right?
Can I ask?
Yeah.
So I talked about how I'm having I'm just barely now digesting the fact that you can put quantifiers into your type specifications. Universal quantifier makes sense. I mean, I sort of described how that would work in code.
Yeah.
Existential, though, I don't get at all. Like, I have no intuition for how you would use an existential quantifier in a type description. So
I think of it as the sum, infinite sum. So think of instantiating a C, let's say C1, then it is CS of C1, blah, 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 or C of, C2, blah, and so on, right? So it's a sum type.
Sum overall.
Yes.
All types.
When you create one, you have to specify what C is and then give the value. When you are using it, you don't know what C is, so you have to make sure it works for all C. And you can kind of think of it as a big triple in that case, where you sort of say you get C, you have a C, and then that CS, C cross A, it's I don't know, just trying to say that the exist is sort of like another element of the tuple.
Here's what I would say. What Yoneda is saying is that this is like having an infinite disjunctive union for all possible types C of this. So it's kind of, imagine you have int to A, B plus int, plus Boolean to A and B plus Boolean. And plus, and all possible types here instead of C. So it's a huge disjunctive union where C goes over all possible types, including all possible parameterized types, including everything. Not just primitive.
I have a question.
And this, this means you have f of int and f of Boolean and f of everything else.
Yeah. Okay. Can you give me like the first example of a existential quantified type, which is useful for something?
Well, maybe is an existential quantified, right? A simple example.
No, I don't think so. Why do you say
no?
Because I can write that as a finite sum.
Oh yeah, that's right. It's finite. Yeah.
Yeah, you need this infinite sum, and so yeah.
So I mean, there's some in the paper, but they're complicated enough that it's hard for me to grasp them right away.
I mean, you can think about, first of
something like representation, a function where you can convert something into a string, right?
Okay, here's one example, right? So
it takes
you have a pair of exists C, pair of AC, right? The only thing you can do with it is extract A. You cannot do anything else. So this is a data type which is given to you, and you know it's a tuple, and you know it has a one part of type A, and you don't know what
it's an A with something else of some type.
Yeah,
you don't know.
You have something else in it, but you don't know what that is.
Okay.
And there's no way for you to know. So it's opaque, so you know that it's in there, but you can't take it out because you don't know what type it is. The only thing you can do with it is copy. So you can create, for example, you can have a function from this to like this, right? And if you have a function from A to B, then you can have a function from this to this, where you transform the A and just copy the C into D. You just say D equals C. Because when you produce a value of this type, you're allowed to choose this type as you want. But when you're given a value of this type, you have no idea what that type is. You cannot extract it because you don't know what the type is, but you can copy it. And
so maybe another example would be like exist C, paren C, comma, C to A.
Yeah.
Right. So this is something where you don't know what that type C is, and there's going to be some value of that type in there, but you also are giving a function that allows you to kind of turn it into an A. So you can actually do something with that.
Yeah. So you can write code that takes this as an argument. So you can take X of this type, and then you have like first of X, and then second of X applied to the first of X. And this will have type A. And so because you know the type A, you can get it out. So
cool. Young-Il, you had maybe a different example. Was it somewhat similar to this?
Yeah, I was wondering if you had a function called string that can take any type object and represent a string representation of it. Is that an exponential type, or is that a universal quantification type?
You have a function string that can take a value of any type?
Yes, of any type, and produces a string representation of it. Is that existential in A, or is that universal on A?
It's more like universal.
So I would say
Okay.
this, you can write it down both as universal and an existential if you want to, because this function actually needs to produce a string out of every possible type, right?
Right.
So the string is like integer to string and Boolean to string and everything else to string. It's an infinite product. And so you can say this is an infinite product. So this for all A, A to string. But infinite product of this kind is equivalent to a function from infinite sum.
So right, because A is on the left, that's equivalent to exist A to string.
Because you can write it like this.
Okay.
And so that is now exists A
dot A, I think, and then parens around that. Yeah.
Because this is like this, the parens.
Yeah.
And so actually they used this transformation at some point in their paper, where they went from existential to
universal to existential on page 13.
Yoneda, when they introduced Yoneda, maybe.
Yeah.
Yes.
That was confusing to me.
Yeah, on page 13, go back to page 13.
Yeah, middle of page 13. There we go.
Right.
How can you have the exist A in that data a little bit further down, the exists A, I thought that should be inside the constructor. Go down a little bit, see where it says data koyo, right there.
You mean here?
Yeah. How can you have the exists outside like that instead of inside?
Well, koyo is not a function. It's just a
It's
label.
a constructor.
Yes.
So you're saying that their exist A should be right in front of the function f?
That's what I was thinking.
Well, it is in some sense right in front of the function f. I think all this is just syntactic noise.
Yeah,
These are just
Okay.
names.
which is
in
giving
Haskell,
names. Yeah.
It's just that in Haskell, you would write, very confusingly, you would write for all in here.
Yeah, that's the other thing I'm worried about. So when I
Yeah.
see for all in Haskell, I should imagine an exists.
Well,
Well,
you can say,
koyo is sort of a function that yields a koyo, right? So
yeah.
and exists over the whole thing is for
So-
all on anyway.
So if you don't say for all, it means universal quantification. And if you say for all, it means existential quantification
That's
in
right.
Haskell.
Yes,
Oh, that is so counterintuitive. Okay.
yes, that's how it is.
The first part is intuitive, but that second part, yeah.
Okay.
Hmm.
Now I get it when I see for all in Haskell.
Yep.
Okay.
So yeah, so essentially this, you could say this for all is outside, and it is converted into existential inside.
Mhm.
But Haskell just chose the syntax. So, but I agree that this is confusing. So this existential should be inside somehow. But to me, this is just very confusing to have a lot of names around the type.
Right.
Because these names actually are functions that take what is inside as an argument.
Mhm.
So, but I don't want to define functions at the same time as I'm defining a type.
Yeah.
Yeah, this is it's the
Well-
Haskell record syntax. This took me a while. I have seen it, but it took me a while to figure out how to apply it. In this case, the curly bracket.
Yes,
Um,
right.
They're
Yeah.
basically saying that the state of this thing is f of a cross a
Right.
arrow r. That's when you
Yep.
create one of these things, that's what you have to give.
so you can wrap it up
And when
and
you
get a
take it
koyo.
apart,
Right.
you can to take it apart, you use the unkoyo, and that will give you one of those.
Right.
Now,
But the syntax is weird. Yeah.
They just wanted to have a very short syntax that defines everything at once. It defines a type, it defines the names of the type constructors, it defines the functions that give you the destructuring, and so on, everything at once. In Scala, you would have to write it much more verbosely. You would have a, so existential type in Scala is where you have a case class that extends a trait. So say I have a trait with some type parameters, say, and then I have an existential, which is, sorry, not B, type class must be something like B1 of AB extends P of A. So this is what you would have to do in Scala. And so this B is inside this case class, but it is not shown on the trait. And so when you create a case class, you have to say what this B is. But
when you
outside,
create an instance of that class, you have to specify B.
if you want to create a value of this type, the only way to do that is to create a value of this type. And then you have to specify what B is. And there could be data of type B inside there.
Right.
So you could implement this Koyo, for example, in this way. But this B will be only visible to you when you create a value of this type. And then to the users, it's invisible. So they cannot get a B out. They don't know what B is.
But
So
that trait has basically an unkoyo method, right? Something like that. So that you can get it out.
Well, you can. I'm not sure if you want this koyo and unkoyo, but essentially, you cannot get out what A is in the sorry, what B is. Yes. So here's what I would write for koyo. Actually, let me make this bigger. So I would say case class koyo of, let's see what that must be.
Wait, wouldn't that be the trait? It's
FR. Okay, yes. So sealed trait koyo F R final case class. I'll have to have a name for it, like koyo1 of F R A. And inside this, I would have to put this data. F of A and run A to R. Extends koyo FR. So if you write code like this, the result is that you can create this koyo only if you create this. When you create this, you have to specify what A is and give some values of type F of A. But once you have done it.
But the problem is once you've done that and you have, it's just a koyo, not a koyo1, there's nothing you can do with it. Because that's why I'm saying there needs to be a method on that field
So
trait.
let's define methods, but you define a method here. Yes, let's define it. Like for example, get, you can get F of R out of here. And here you would define this get.
Why is it F of R?
Well, that's what you can get out of this. If F is a functor.
But okay, in their definition, there is the unkoyo, which gives you the two components, right?
Mm-hmm.
The object unkoyo, the first parameter is of type F of A, and the second type is of A into F R. So you can apply that function. So
yeah, the problem is, you can apply that function, but you can only apply it. I'm not sure how Haskell does it.
No, you can't apply it because the first component is of type F of A, not A.
That's right.
And then the second one is a function from A to R. So there's no way to use that function that you get. That's interesting. Why would you even have it then if you can't use it for anything?
So here's what you can do. If f is a functor, then you could get fa dot map run.
I see.
Then you could extract this f of r out of here. Even though you don't know what a is, you can still do this.
I see. Okay.
But you see, in Scala, you would write this code in this case class where you have the a.
Yeah.
You cannot write this code here. Because you don't see this a, and so you don't see the structure if you're at this level. Now in Haskell, I'm not sure how they handle this problem, but what you can, but what if f is not a functor? Then you could not do this.
Yeah.
Right, so what can you do with this? Well, you can define a map method on Koyo. R to S, Koyo FR, Koyo FS. So you could define this function like fmap. Even though you don't, so how do you do that? Well, you have this function a to r, then you have r to s. And you compose them. So then you get a function a to s instead of a to r in here. So again, you have to define this fmap in the trait as an abstract, and then you define it concretely in this case class, where you have, so this case class essentially is where you can write code using the two parts. And note that in this case class, the parameter a looks like it's universally quantified.
Yeah.
So you're kind of inside the unkoyo when you're writing code here. When you're writing code here, you're kind of inside this unkoyo. But I don't know how Haskell handles it. So there's this problem where you're, for example, you cannot get this fa out of this function alone. Out of this value, you cannot get alone f of a. Because
you don't know what a is.
You don't know what a is, exactly. You cannot type the result. And
now,
the type system, yeah.
Scala does have an explicit existential type, right? You can say something like for some.
Yes.
Yeah, and then
it is not.
Go ahead.
Yeah. It is deprecated now, but yeah, it exists. Yeah, it is deprecated. I don't know the details of this. So this was used only in some very limited circumstances. It is not the same as this encoding of existential. It was used only for some Java API compatibility, where I forgot where it is. Nobody uses it really in code.
Okay, good to know.
But yeah, it exists in Scala in general, but it does not exist in Scala 3. And so existential is encoded like this in Scala, and it is encoded like this in Haskell.
I mean, the other thing you could do with Scala is have a record that has a type field in it. So you would,
yes,
maybe, make your trait have, the A field as well as the other stuff. But it's abstract. Right.
I should leave soon, but we should set an agenda.
Oh, yeah.
Right.
Do we want to do more of this? there's a fair amount of stuff in between. I don't know. You know, examples of Yoneda, you know, those things, but maybe more interesting is like how double Yoneda works, and I don't know.
So shall we do that in 2 weeks?
Or do we have something else to do?
There's something else on our stack.
Which is?
Oh, I just there have been various ideas floating around.
Oh, right.
I don't remember one that everyone was keen on, but I don't remember the whole list either. So.
Okay.
No, I would be happy to chew on this a little more. I feel like I understand most of this paper, like probably about 60% of it.
I still don't understand how you get from type class to specific types. But anyway, I'd like to understand that. I mean, it's kind of mysterious. You have a type class defined with some kind of weird method. Why is that forcing you to have a specific, you know, lens or prism or something else? Anyway, I would be in favor of finishing, have one more meeting on this paper. And we can discuss, but does anyone else have other preferences?
I'm thinking maybe let's focus on 3.4 and 3.5 and then section 4. 3.4 is the universal and existential thing. 3.5 is, where'd it go? Representable functors. I think that's interesting. And then, you know, section 4 is all the profunctor optics, starting with double Yoneda and a lot of the stuff. Some of the stuff that we just talked about, I guess. But I'm still need to think it through.
I found another related paper. It's called Profunctor Optics, a categorical update, and it's dated January of 2020, and it has like 7 authors, 2 of whom are Jeremy Gibbons and one is Bartosz Milewski. So I was thinking, I looked at it to see, will it provide any intuition, a little bit better intuitions, but I'm not sure. It seems to use, anyways, I can't remember where I got it. Let me,
what was it called again? An update, something?
Yes, it's called Profunctor Optics, a categorical update, and it's on archive. So maybe I can, I don't know how do I copy the archive location? Oh yeah, here we go. Let me see if I can add it to the chat.
Okay, yeah, that worked.
We're in the Slack channel.
Oh, in the Slack channel. Yeah. Okay.
Yeah,
got it.
and it will stick.
Okay. I try to do a copy, but it's not. Here we go.
It's easy to find this paper.
Yeah, the link. Yes. I was able to get to the link. Okay, so on the Slack channel. Okay.
Well, I'll check the Slack channel, and by default, I'll just keep forging ahead with this paper also.
Yeah.
All right.
We can discuss both. Okay. All right.
Thank you.
2 weeks.
Okay.
Adrian?
Thank you. Ciao.
2 weeks is good. All right. So.
Okay. Good.
Rest of this paper and the next paper.
Yes. Cool.
Okay.
Thank you.
See you in 2 weeks.
See you.
All right.
Bye.
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 Yeah, thanks, Sergey, for pulling us through this.
Well,
Yeah.
I'm very interested myself. Anyway, thanks.
Great. Okay, bye.